Okay, in the last session we learned about the vector operators or the operations that are called gradient and divergence and its physical meanings also. Now there is another important thing which do not have enough much important in electrostatics, but which is very important when you learn magnetism, that is called a curl. But anyway, as a part of the for the completion of vector calculus, I am discussing about curl also. So let us see what is curl. So curl is expressed as some del cross E is equal to x cap y cap z cap, then the determinant of x cap y cap z cap, then dou by dou x, dou by dou y, dou by dou z, and Ex, Ey and Ez. What is this Ex, Ey, Ez? We know that we are taking the cross or a cross with a vector field. For a vector field, let us suppose it is E, and for E is equal to Ex, an x component x cap, plus Ey y cap, plus Ez cap. That means a single vector function can be converted into three components, and each components comes here. Ex will come here, Ey will come here, and Ez will come here. So what would be the result of that? Yes, exactly as the name suggests, curl. Curl means something to curl around or rotating, or that is the meaning of curl. So it is a measure of the curl of a vector field. That means how much it rotates about a point. So it measures the rotation about a point of a particular vector field. For example, you can see here the vectors are actually rotating around this ball. That means something like a wind or something, it is turning here. So here you can have a turning here. So it is actually curling out, and if we calculate the curl of this vector field at this point, we will get a positive value. That means if the value of the curl is 0, then we say that it is not a curling vector, or we call it as it is an irrotational vector. But for a vector field like this, there we have a curl. The best example that we already learned in the +2 classes, we mapped the magnetic field due to a bar magnet, that is something like this. You already learned about this. Okay, we practically drawn it in your +2 classes, and as you see here, this has a curling effect. So the magnetic field has curls, but so actually it is completing, the field lines are completing through here. So this is a curved or a rotating kind of vector. So the magnetic field, for a magnetic field, the del cross B has a non-zero value, but in the case of electric field it is 0, that we will calculate it later. Anyway, curl measures the rotation or how much a vector curls around an axis, that is measured by the curl. Okay, now let us calculate a curl for a particular vector. So these are some examples. Here you can see that it is rotating. So to find whether it is curling or not, you can imagine a paddle wheel. That means something like this, a fan leaf like thing. So you can place some fan or a leaf of something, that is called a paddle wheel. You can imagine that this surface is a fluid, surface of a fluid, and there is a flow like this. And to measure whether there is a curling, that is a non-zero curl, to measure that, just place this leaf or this paddle wheel here, a fan here, and if this rotates, that is due to the flow of this fluid, due to the rotational flow of this fluid, if it rotates, then we can say that there is a curl. If otherwise, if there is no rotation, you can see if it is a uniform flow, something like this, they are all parallel, the flow is all parallel. If you place a fan like this here, it won't rotate actually. So there is a non-zero curl. So this is the example for, this is the simple way to imagine about curl. So now let us see another one. So this is the another one. Here you can see there is no rotation actually. That is, they are all in straight lines. There you cannot see any rotation. But actually, if we calculate or if we find it mathematically, this field has a curl effect. So let us check it out with our paddle wheel experiment. Let us place a paddle wheel here. So let me put it in color. So let us imagine a fan or a paddle wheel here. So, this is here. Now, imagine it is a fluid flow, all the arrows represent the velocity of some fluids. Now, here above the y-axis, so or above this side, you can see the fluids are flowing along this direction, that means along negative y direction. So, this fluid will exert a force on the upper part of the paddle wheel towards here. Now, check the lower part. So, let me draw the same paddle wheel somewhere over here, okay, to represent the force. So, this is it, okay, this is our paddle wheel. Now, for the upper part here you can see that is a force is experiencing because the fluid is leftward in the upper part. So, the flow will be towards here. So, this paddle wheel will experience a force towards here, here also it experiences a force towards here. Okay. Now, what about the downward part or the part below the y axis? That means it is actually not below the y axis, it is on the xy plane actually. So, just to the reference I said it is below this line. So, here you can see the flow, the direction of the flow is towards here. That means the paddle wheel experience, this wheel or this leaf will experience a force towards here. That means actually you are pulling one of the wheels towards here and the other towards here. So, what would be the resultant effect if we pull something like that, this will rotate. So, even though this vector field particularly appears as do not have a curl, but it actually has a curl, that is why the paddle wheel experience two equal and oppositely directed force and which causes the rotation. So, that rotation means physically it is a curl. So, if we calculate del cross E for this particular function, we get a non-zero value. Now, as an example, let us calculate the curl for a particular function, that is nothing but v is equal to minus y x cap plus x y cap. So, this is a particular function, that is y into x cap, that is there is an x component part and a y component part. So, we can write it as v is equal to v x into x cap plus v y into y cap plus v z into z cap. That means by comparing it with, we can find each component. What is the component Vx? So, we got Vx, that is what is associated with the x cap. Here associated with the x cap there is a minus y. So, that is minus y. Now, Vy, what is Vy? So, Vy is the part that is associated with the y cap, that is x. So, that is we got x. And what is Vz? There is no Vz, that means it is 0. So, now we have the determinant here, that is x cap, y cap, z cap is the first row, then dou by dou x, dou by dou y and dou by dou z as the second row, and for the third row you have to substitute Vx, that is you can substitute Vx here, that becomes minus y, and Vy here, that is x, and Vz is 0. Now, just evaluate this determinant. It is very simple, you can do it, that is x cap into dou by dou y of 0, dou by dou z of x, this becomes 0, y cap when you calculate it will be 0, and for the z cap you get it as 2 z cap. So, as you see here, you can see here we do have a positive curl and it is curling around the z axis. So, let us see its image. So, this is actually the image. If we plot it on a plane, okay, you will get the image like this. So, without using that image or the paddle wheel or imagining anything like that, from the functional form itself we can calculate whether it will curl or not, and the same thing we can infer from the graph also. So, this is what mean by curls. So, curls will give you how much a vector rotates around a point. So, that is curl. Now, we have three operators, that is gradient, divergence and curl. Now, let us connect them using some other laws, and before that let us learn a bit about the integral calculus. So, here we were dealt with only derivatives. We had an operator del which actually consists of some partial derivatives, dou by dou x, dou by dou y and dou by dou z, and we learned about its operation. So, this much is simply this is a very precise form of differential calculus. Now, we want to learn about the integral calculus, how to integrate through a vector field. That is also there are three kinds of integration, the line integral, the surface integral and the volume integral. So, let us go to line integrals. Okay, line integral. So, let us see, simply the form of the line integral will be something like this, a to b v dot dl. So, sometimes there will be an L or a path row or something will be written as a suffix here. Otherwise, from this DL, that is here you can see a DL, it has a vector nature. So, this DL, this shows it is a line integral. So, how to identify whether it is a line integral or surface integral or volume integral? Just look for this differential thing. So, this is a line element. So, we are doing a line integral. So, what is that line integral? Let us see. So, here we have a space here and I want to do a line integral from A to B. So, A is a particular point in space and B is a particular point in space, and in line integral we are actually doing it through a particular path. So, to denote that we can write a P here, we do it along a particular path, that is from A to B. You can have infinitely many possibilities to go from A to B. This is one way. So, or you can move something like this, we can move something like this. In general, each path, so I can evaluate the line integral through this path or this path, but in general each differs. But there are particular cases where each of the integral, if or the integral is independent of path, there are such integrals or functions are there. So, before going into that, before discussing that, let us see what is a line integral. So, we are choosing this, not going into many, we have a particular path. Okay, now let us see what is a particularly a line integral. So, we have a path here. So, what we are evaluating is v dot dl. So, what is this v? V is our vector function and that vector field is spread out all over this space. That means here we have an z, y and x coordinate, this represents a space and all over this space there is a vector function v. That means at each point there will be a vector. So, when we calculate v dot dl, what we are actually, I am not going to the integral part, I am just calculating v dot dl. So, they are both are vectors. Now, for that I choose a particular part of, that is I can divide the entire path into many different dls, many different many different pieces. Each of them can be considered as a straight line with a direction. What is the direction? We are moving from A to B. So, we have to start at A and end at B. So, this will be the direction. So, let me take this part along. So, if we look closely into that part, you have a point A. So, at point A there is a vector like this. This is a dl, that means a part of that entire length. So, that is dl. dl has a direction like this. Now, let us consider v. So, at the same place we have a particular value for our v also, because it is v spreads all over this space. So, at this point also our v has a value. So, let that value, that is a vector, be something like this. So, this is our v and this is our dl. So, we can take v dot dl. So, we are calculating the amount of v, okay, the v is actually along this direction. Now, v dot dl means we know that that is v dl cos theta, and what is theta? Theta is the angle between them, okay, v and dl. So, we are actually picking out the particular component of v along dl. So, we got at this point we get v dot dl, that means the amount of v along this direction. And in the next piece we take, what is the next, the direction of the next piece is like this, and v will be along some other direction. So, this is v, this is dl, and again we pick out the component along this direction. So, we are actually picking up what is the component of v along that particular direction and summing it up along the path. So, this may sounds not familiar to you, but you know it is exactly what it is when we learned work. So, we know that what work is F dot dl, force into displacement, and there you probably written ds. This is not to denote the surface, but this is what is called a displacement. So, integral F dot ds is called the work done. That means, if you are moving an object through a particular path, so through a particular path and you are applying force, but the force applied need not be along the path itself. Here the force may be you have applied through this direction, this is the direction of force, but it moved through this direction, maybe because of component of force or something else, constraints are there. So, anyway, here the force is in this direction, but it moved through this path. So, they may differ. Now, what is the work done? Actually, the work done is the component of force times the displacement, component of the force along the displacement. So, to calculate the component of the force along the displacement, we use F dot ds, and to find it for the entire path, we have to take the sum F dot ds here, F dot ds here, F dot ds. So, for each segment we have to calculate that and sum it up. So, to sum it up in that way or infinitesimally we are summing up, we use integral, that is integral a to b f dot dl. Now, there can be another type of this, so the same thing. Now, the endpoints are the same, that means if the endpoint are the same. For example, I can start from A, go to B, and I can come back to A. That means I am starting from A and coming back to A. So, the end points are the same. That means we call it as a closed integral. That means the path is closed now. Okay. So, this is called v dot dl. Now, whenever you see something like this, you have to notice that the end point and the starting point and the ending point are the same, or the integral is taken over a closed loop. Okay. So, this is. Now, there is something else which I have already trying to say, that is a to b v dot dl we can do through different path. Let it be through a path 1, and I can do a to b v dot dl through another path p2 and p3 etc. So, they need not be the same, but there are specific type of vector fields, that is this kind of v's, for which the path whatever be the path chosen, the value will be the same. So, there are some kind of force fields or the field are there, and they are called the conservative field. So, we have already learned that when we learn the force, there are a certain kind of force that is called the conservative force. For conservative forces, the work done will be the same whatever the path you follow, or the work done is independent of the path. So, then we call the field or the force F as a conservative. So, the same thing can be applied here also. We can have conservative field. Such an example, a best example for that is the electric field that we will discuss after this, when we again getting back to electrostatics. So, this is about the line integral. Now, there is another thing called the surface integral. Now, in surface integral, actually you can identify it from this S simple or dA. dA means that is an area. Now, v dot dA, what is that v dot dA? Some similar kind of this actually we have learned when we learned flex, where E dot ds we found it as phi. So, phi is equal to E dot ds, which is familiar and we learned the previous classes, that is called a flex. Now, this is similar. There is only the difference is that there is an integral. That means integral does not mean nothing complicated in that, that is just means we are summing up over an entire surface. Now, imagine this is a large area and we choose a particular part of it, that is called dA. Now, we have a vector field here, and that vector field will have another direction v. Okay. Now, we can find the component of that vector field along the direction of dA, or in the terms of electrostatics, we found out the electric field. So, we had an area and we have some electric field passing through here, and which is not perpendicular, and let's and the direction of area be this. And now, by definition we know that electric flux is the number of field lines passing, or the electric field passing normally through an area or perpendicularly through an area. Now, here you can see this is the direction of the area, that is ds, and our electric field is not passing perpendicularly. Now, how will we calculate the flux? We will pick out the component of electric field that is normal to that area. So, to find that particular component, we used something called E dot ds and we called it as flux. So, phi denotes flux. Similarly, v dot dA is also called the flux of a vector field through a particular area. And we done it for a small elemental area, and we can do it for a very larger area, and we have done many similar example while calculating or while applying Gauss's law. So, there is no need to mention it more about that. And V dot dA, we know that that means the surface is closed, that means over a sphere, over a cube, over a cylinder. We have already done many examples of that, and that is V dot dA, that represent a flux over a closed surface. Okay, that means why we call it as flux. Flux means actually the flow of something through some area. Actually the name comes from fluid dynamics, that is, it means that something is moving or something is flowing across the area. The amount of that fluid flowing through a unit area per unit time is called a flux. Actually this is the amount of that in fluid dynamics, but in electrostatics we call it as electric flux, and that is it. That is why the name flux. Okay, that is the flow of something through a unit area in unit time. So that is about surface integral. Now there is something else called the volume integral. So the two of them before, that is, there is a surface integral and volume integral, which had a vector nature because we took dot product, but in the case of volume integral there is no vector nature. We always calculate T d tau, or we calculate here this T will be a scalar function. The best example is, imagine you have a mass or you have a lump of charge here, okay, a charge distributed. Now we want to calculate the total charge. So what we do, that we know the charge density, and the symbol for this is rho, okay, and what we do, we took a very small piece of that, okay, and the very small piece has a volume d tau. Now this is the charge density and this is the volume, then the product will be dq. So when you product it, you will get dq. Okay. Now to find the total charge, what we do, we find many of the pieces, or we divide the entire volume into many small such pieces and we will integrate them. So we integrate it to find the total charge. The best example is what we have done, the same thing we have done in the application of Gauss's law. There is another example. For imagine that you have a volume, and in the volume there is a mass density. So we can choose a particular volume here. Now we want to find the total mass of this object, then we can do rho d tau integral. Now here this rho is the mass density, this will give you the total mass dm, integral dm will give you the total mass of this. So this is the example for volume integral. So there are three kinds of integral: surface integral, volume integral, and line integral. So now we have some fundamental theorems that connects between the endpoints or the integrals, that is, a line integral can be connected with its endpoints and a surface integral can be connected with its end, and that is a line, and there is volume integral which is enclosed by a surface. So we can connect with a volume and a surface, a line and its endpoints. So such three theorems are there. They are known as the fundamental theorems in integral calculus. Let's learn that too, because we need that many times when we are dealing with electrodynamics. So let's go into that. Let's go to those theorems. Now here you can see here there are three fundamental theorems are there. That is, one is the fundamental theorem for gradient. You have to read it like this. The first law, we will explain this law later, and this is three fundamental theorems, and the first one is the fundamental theorem for gradients, and the second one is the fundamental theorem for divergence, and which we derived earlier for the representation of Gauss's law in differential form. We actually derived its form. We are not going to derive this gradients or something. We can you can learn it from some classes on vector calculus, and this has a particular name called Gauss's theorem or Gauss divergence theorem. And there is one more, that is the fundamental theorem for curl, that is called the del cross V. So okay, we will go to that later, and it is called Stokes theorem. Now here you can see something, that is just avoid this expression del t, del dot v, del cross v or any other. Actually what it does is that here it is an integral, it is a line integral, and that line integral is connected with the t of b and t of a. That means we are evaluating a line integral at some point or at some vector field, and that vector field is del t actually, not just t, it is del t. Okay. Now we know that the end point of the lines are a and b. So, instead of doing the integral whole way from here to here, we can just calculate it by measuring the endpoints, that is t of b and t of a. That means a single line, left side is a line, that means a line integral. That line integrals are two end points. So, a line is enclosed by, we can imagine like that, a line is actually enclosed by, that enclosed means what are the endpoints. So, enclosed by two single points. So, here the line is connected to A, B and A, two endpoints. So, each of them, when you analyze each of these laws, we are actually connecting a particular geometrical form to its endpoints. Okay. Now, the line has endpoints, a line has ends as 2 points. Now, what is the left side of this? This is V dot dA. So, before going to that, let us talk about this Stokes theorem. That is, here you can see this is a dA, that means it is a surface integral. So, surface integral has to be connected with what? How? A surface is actually, so suppose we have a surface here. Actually, what I have drawn here? Just a line, and I say that it is enclosed by this line. So, a surface is enclosed by a line. So, here a surface integral which is connected to its enclosure, that is a line. So, surface is connected with line, and here you can see this is a volume integral. That volume integral is connected with the surface, because if you take a volume, to consider a volume itself, you need a closed surface. So, we are connecting it with a closed surface, and we need a closed line to represent. So, we are actually connecting with the ends, okay, a particular geometrical form and connecting it with the ends, and each of them has a specific meanings also. So, we will learn about specifically each of them. Let us see, this is the gradient. So, this is A to B del t dot dl, that is t of b minus t of a. Now, what does it mean? Imagine that you are standing in front of a big tower, something like this. So, you need to measure its height. Okay, imagine this is something, a kind of Eiffel Tower or something. So, you want to measure its heights. What you can do is that, you know that what is del t? Del t is the change in that function. So, here we want to find here our function, or we want to find the total height from here to here. What is the height that we want to calculate? So, you can do it in two ways. Either by measuring what is the change you can let me draw it as a single line, that is better visually. So, we want to find the height of this. So, for that what you can do is that you can make it into different pieces, and you can climb with a scale, and we are measuring this. What is the change in height here? What is the change in height here? What is the change in height here? And we are actually adding up all this. Actually, in a straight line you won't feel that, because it is a straight line. Here let me take another shape, something like this. Suppose this is my shape and I want to find the height of this. So, what you do? So, you can split, okay. Now, you can split it into different portions, okay, some 5 or 6 portions, and you can calculate del t. What is del t? That is the change in height. In the case of height, this becomes del h, that means the change in height. So, when you go from here to here, what is the change in height? That is first del t dot dl, okay. So, del t, del t dot dl for the first one. So, that is here we calculated. Then for the second step, so plus del t dot dl for the second one, and third one, the fourth one. So, in each step we are actually calculating the increasing height, and we sum it up together to get the answer. That is what we actually do in the left side. So, instead of that, you can do something else. You just pick out something called altimeter. So, altimeter is something called something that can be used to measure the altitude. So, what is the height? Now, you just stand here with your altimeter and look for the reading. Let us see that it shows the height of you, or the height of that instrument from the mean sea level. So, let it be 32. So, 32 meter or something, and you climb with the same thing to the end point, to here, and again check the reading. suppose it is some 120 meter. So, now what is the height of this? So, simply you can minus 120 minus 32. So, it is very simple. If you know the values at the endpoints, just minus them and you get the value. The height at the final point and height at the base, just take the difference to find this. So, that is the essential thing or the cream of this law. Instead of calculating it bit by bit, you can calculate it is by measuring at the endpoints. So, that is about the gradients, but here you have to have a changing, that is here you have to have a gradient. You cannot convert every integral to like this, you have to have a form like this, then only we can convert it. Now, let us see about the next one, that is Gauss divergence theorem. That is the fundamental theorem for, that is Gauss's theorem or Gauss divergence theorem. Here this is something, that is we are actually connecting something called a volume integral and a surface integral. So, imagine that you have a balloon or an elastic ball or a balloon, simply a balloon, and that balloons, inside that balloon or ball, imagine there is a ball, there is a plastic ball or something, and imagine inside that there is a source of water, and actually water is coming out, but you cannot see that, you cannot see what is inside that. There is some water source inside, and what you only have, you can see it from outside, but outside there are some holes for this balloon. This is a porous ball, not a balloon, it is a porous ball, but you cannot look through, you only see that there is some flow coming out. So, here is some flow, here is some flow, here is. So, you do not know what is inside, but you only see some water is coming out of the surface, you see only the surface. Then from that you can measure what is inside. That is actually the essence of this. Let me explain. That is, what is this V dot dA? That is the surface integral or the flux. That means if you go to the surface of it, so here you have a surface, many surface, that means totally a spherical surface, you can calculate the total flux coming out of it. Okay, something is coming out of it, you can make a measure of what is coming out of the surface, and from that you can infer that there is something diverging out. That means if there is a flow through a surface, through a closed surface, there should be something inside that. So, that something inside will be del dot V, that is, if that del dot V means there is something diverging out, a water has to be diverging out. Okay, that can be measured with this. So, instead of going into that, okay, instead of going into this ball, if you cannot, something like a black box, you cannot go inside, you have to learn what is inside from what is coming outside. That is something we calculating here. So, this is actually our Gauss's law, that is this become del dot E, that is rho. Actually Gauss's law and these are the same exactly. Now, let us go to the next one, that is the last one, that is called the Stokes theorem. So, this is called the Stokes theorem. Now, let us see. So, Stokes theorem connects del cross V dot dA is equal to dl. So, we can calculate, it is a very simple law, that is you have an area like this, okay, and we want to calculate the curl. Curl means the circulation or the rotation of a vector over the surface. Okay. So, for that what we do, we have to split this into many infinitesimally small pieces of area, and for each area you will calculate the amount of curl. So, here how much it curls, how much it curls, and how much it curls, and we calculate all of them. And finally, so let me draw one more row, this is the reason for that. Okay. Now, I draw all of this and calculate the del cross V dot dA to calculate the total curling effect over the surface. So, instead of that, instead of going at each of this, you can evaluate its line integral. That line integral actually goes exactly through this line. So, how it actually happens? Let us see, we draw it in something like this. Okay. So we have to calculate, we can calculate this line integral. So before that, let's look into that. So let me draw. So how it actually physically we can learn that, or we can. So this is 1, this is 1, this is 1, this is 1. So I am splitting it into almost 9 circulations. Okay, now here you see that what happens inside. Okay, we need only the outside. So by this law we know that we do not need to go inside it on each pieces. You have to only go for the outside, what happens at the edges. So here you can see that here the direction of this, so the direction of this is to here. Now here you can see the curl is to here, and just below that there is another curl or an area which has a direction towards here. So one is directed to here and one is directed to here. So inside they will cancel, and you can see here also, here it is directed to here, it is directed to here. One is, if I so if I take that portion particularly, one is like this, one is like, they will cancel. So what happens is that the total in the inside part will cancel. What remains? What remains? Only the outside part, that is this circulation. So we get something like this. Instead of calculating each of these pieces, you can calculate the total line integral along the surface. So that is integral del cross V dot dA is equal to 0. And there is one more thing. Here you can see this is a line integral and this is a closed line integral. I already told you that there are some functions or vector fields for which the line integral do not depend on path. For that cases, the closed integral becomes 0. That means V dot dl becomes 0. For such functions, we can see if V dot dl is 0, then we can see that del cross V is equal to 0. This is an important result that we need in the next class. That means if you have a vector function, that is some let it be some V dot dl, some V dot dl, and if that V dot dl is 0, then automatically from Stokes theorem this right side becomes 0. That means the del cross V is also 0. So from this result we will go to something new called the potentials. So that we will discuss in the next class for a backing up or for learning that why we learned all this vector calculus. So you have to take a better course or a detailed study on vector calculus, which is very important while learning electrodynamics and fluid dynamics and many topics in physics. So it is very important to learn that. And now here we are summing up, or we are ending up the session of that mathematical physics, and we will start the physics part in the next class. Thank you.